Hello, my name is Andrew Chang. I am a third year ECE major, and I took this class because I was really interested in data science, and I wanted to learn more about machine learning.
Hi, my name is Anastasia Yang. I'm graduating fall of 2024. I took this class because I wanted an introduction to data science and machine learning. So, yeah, and then a fun fact is that I have two cats.
Hi, my name is Armand Kosawala. I'm going to be graduating next spring in 2025. And my fun fact is, I'm taking this class because I wanted an introduction and also to fulfill a requirement. And my fun fact is I make my own yogurt.
My name is Joaquin, and I'm a junior doing ECE. And I took this class because I'm pretty interested in data science. I wanted to get a good introduction, and I think it's going to be pretty revolutionary. So I wanted to get a good introduction to it. And my fun fact is that in 2016, I went to a gaming convention and I won an Xbox.
Oh, that's really cool. Hi guys, my name is Juan Gonzalez. I am graduating in spring of 2025, and the reason that I took this class was because my friends were taking it. Wanted to see if it was going to be interesting. And spoiler alert, it was really interesting. Anyways, here we go.
We did our project about discovering brain tumors using different data science models. So, for a quick introduction, brain tumors are abnormal growths that can arise from various cells within the brain, and this can lead to a range of symptoms, and it requires specialized treatment. So, brain tumors can either be benign or malignant, and they affect the people of all ages, including like children to adults and elderly. Um, While some brain tumors are slow aging and they don't cause immediate harm, there are others that are like very aggressive and need like urgent medical attention. So, diagnosing a brain tumor involves a combination of imaging tests like MRI or CT scans. Um, there could also be like a neurological exam or a biopsy to determine the type of tumor and its characteristics. So once someone gets diagnosed with a brain tumor, the treatment approach includes surgery, radiation therapy, chemotherapy, or a combination of all of these methods, depending on the tumor specifics and the patient's overall health. So we wanted to improve the healthcare system by having a method to quickly and accurately diagnose complex conditions like brain tumors. And our goal is to develop a model that can analyze brain MRI scans and identify the presence or the absence of brain tumors.
Okay, so the data set that we used was sourced from Kaggle, and it's comprised of MRI images showing both brains that have tumors and brains that don't. They're categorized into two distinct groups, being yes and no, determining whether or not that brain does have a tumor or does not. There are 155 total images labeled yes and 98 images labeled no. And to ensure that our model was trained properly, we split the data into 70% training, 10% validation, and we set the 20% remaining aside for testing purposes. And we also performed some minor data augmentation, which you can see in the following pictures. Uh, So these are examples of the pictures that we use for our testing, which would be, as you can see in the top left, that it's a brain with a tumor that would belong to the yes group, and the picture to the right of it is going to be a brain without a tumor, so that would belong to the no group. And if you scroll down, we can see pictures that have been augmented slightly so as to increase the variation and accuracy of our data. We did rotation, shear, and blur, which are common methods of augmenting the data to prevent overfitting. Period.
The models we used for wait. Okay. Yeah, okay. So we use a variety of models, and one of them was CNN model, which stands for convolutional neural network. And essentially, this is object detection and wait, how do I say this? Object detection images? Dude, this is
It's a neural network architecture that is primarily used for image detection. So
okay. I'm just gonna raw dog it. I don't know if I'm gonna read the article that much. Okay. Okay, so for this project, we're using a lot of different types of models. And one of the models we're using is convolutional neural network, which stands for CNN. And this is a pretty popular model used for like image recognition tasks. And essentially, we have a neural network with a lot of different convolutional layers and filters. Earlier, there's a lot of sequential layers to this. And the last layer is like the actual classification output. So we have all of our filters, and then finally we have our classification output. And here we have a little demo, or some of the code that we have. And you can see we have a lot of convolutional layers, and we have pooling, and we have some like fully connected dense layers. And then we finally have just, like a classification. And this is the model we're using. So there's a lot of different things you can tune, like hyperparameters and like weights or counts of neurons and layers. So it takes some configuration, but we're able to get some results with this. So when it comes to this CNN model, the training and validation loss and accuracy of the CNN model reveals its performance and learning behavior. And in this case, the training loss remains consistent at 0, indicating that the model achieves perfect performance on the training data, correctly classifying all examples. And similarly, the training accuracy is consistently 100%, and that kind of confirms the model is able to memorize the training data effectively. However, the validation loss fluctuations, it ranges from 0.65 to 1. And this suggests that the model kind of struggles to generalize unseen data. The validation accuracy also varies, ranging from 70.5 to 77%, indicating that the model's performance on new data is not as consistent as on the training data. But I'd say overall, the CNN model appears to have overfit the training data, as evidenced by its perfect training performance, but less stable performance in the validation set. This suggests that the model may benefit from regularization techniques to improve its generalization ability and avoid some overfitting.
Next model we're going to focus on is the VGG16 model, which uses transfer learning. So transfer learning in this context is when a machine learning model is trained on a task and then is repurposed for a second task. So it involves using a pre-trained neural network as a starting point for a new task, and then leveraging that knowledge and transferring it to another task, like I just said. So in specifically for VGG16, it is known for its computational success in recognizing images, and it consists of 15 layers, which I can show off now. Yeah, so these are sorry. Okay, these are the 16 layers. So it has convolutional layers, as you can see here, and then also max pooling layers and top fully connected layers, which are right here. And then finally, it has a softmax layer as its last one. So here in the code, we can see that we have loaded in some of the weights that we need for the VGG16. And then another important part is the dense layers that we're building. And then this prediction layer is how we're turning that VGG16 into the binary classification that we need for our purposes. And then in this code block, we can see that it's going to do early stopping. So this is really important so that the model doesn't overfit on the training data, and it actually performs well on the validation data as well as the testing data. So let me go back to the slide. So here's the training and validation loss on the left, as well as the training and validation accuracy on the right, like we saw for the last model. So these two graphs kind of illustrate that the learning progression and the generalization performance. In the training loss, it decreased steadily from 0.23 to 0.005, indicating that the model is improving its ability to make accurate predictions on the training data. And then similarly, the training accuracy increased from 91% to 100%, showing that the model is learning to classify the training images correctly. On the other hand, the validation loss, as we can see right here, decreases from 0.5 to 0.4, indicating the model is also improving its performance on unseen validation data. And then the validation accuracy, which is seen right here, increases from 78% to 86%, demonstrating that the model is generalizing well to new unseen data.
So for our last and final model, this is arguably one of the most powerful models that we're using. We're using the YOLO model, which stands for You Only Look Once. And so the YOLO model goes beyond just binary classification and actually goes into object detection with bounding boxes. And so this YOLO model that we're using is actually the 8th version of this, and it is open source, so it's constantly improving. What we had with our data set was that we had very limited amounts of MRI scans. We only had around 155 images. So these images are not optimized for YOLO, and so we have to actually manually annotate the data set because YOLO requires bounding boxes for training data. And so we actually use RoboFlow, which is a computer vision assistant tool, to manually annotate our MRI scans and detect where the tumors are actually located with bounding boxes. And so the performance of our YOLO model was limited because of our computational power and our resources that we had. So training YOLO is very resource intensive, and training only 5 epochs took around 2 hours. And we can definitely see better results if we train for longer epochs and if we had more access to computer resources.
So moving on to the application of our model in the real world, there are multiple benefits to like having a model that detects brain tumors. So first of all, it's time efficient. People don't have to manually be looking through these MRIs, and these models can expedite the process of diagnosing brain tumors. Secondly, if you're able to do this on a model, it improves the accessibility to healthcare services, especially those with limited resources or in remote areas. And then because of like this accessibility, you can also integrate these models into our current existing healthcare systems and our electronic medical records. So it'll streamline the workflow of our healthcare industry. This also includes automating analyzing MRI images to allow remote consultations and just expanding the reach of medical expertise. Like moving forward in the future, there's always developing technologies such as enhanced imaging, 3D MRI imaging, and hopefully like future models can work with these newer technologies for a more precise diagnosis. And then lastly, for our model specifically, it would be best like if we trained on more extensive data sets because we only had around 250 images. So if we had more data sets, it would improve the generalizing of our error. And then hopefully later in the future, our model can also specify the types of brain tumors and the sizes of brain tumors.
So in conclusion, we can see that using data science models to analyze situations like the MRI scans using CNN, BGG16, or YOLO is a significant leap in healthcare technology, as we can cut out a lot of the steps, as Anna was saying, of the healthcare process that were very manual and take up a lot of time. But we can see here from the results that certain models have been performing better, and we don't know exactly how well these models will perform in the future, depending on how they may change or become more advanced, especially using the YOLO model, which they did say was open source and increases every year. But as we can see, the VGG16 had one of the best performances. So as we can see, the VGG16 performed the best, while our other models were a little lackluster in terms of what we wanted them to show. But I think for a project that we got pretty decent performance out of most of our models, except for YOLO, which we would have liked to have spent more time or processing power on, but did not have the opportunity. But I think overall from this project, we can see that this has the potential to revolutionize the healthcare industry and make this process a lot more efficient. And we hope that data-driven insights and technology can help make strides towards more efficient and accessible healthcare for all. Okay.